linear transformation from V. Right, so T is a linear transformation from V to V. Okay. In this case, T is called a linear operator. On V. Right, so we will later to describe this situation as that the wind is so strong. Okay, so whenever we mention that T is a linear operator on V, that means that T is a linear transformation from V. So V is the domain of T, and the V is also the codomain of T. In many situations, we will select a basis, right, B, for the domain B as well as for the codomain. Because in general case, we can select a basis for the domain V, and we can select another basis for the codomain, right? In general case, we can select different bases for V here and another basis for V. But since the domain and codomain are the same, so in many situations, that we will select a basis, the same basis, right? For the domain V as well as for the codomain. Okay. So with respect to V, T is a matrix representation. So this is alright. So, well, in general, the matrix representation should be called T3V, right? Because we use the same basis for the domain V and for the codomain V. So it should be there. But we will use the notation TB. Okay? It means that TB, right? So it's just a new notation. And then Tx is B. So a vector in V will have the coordinate vector relative to the basis B. So this is the B coordinate of the X. And this is the B coordinate of the image here. Okay. And these two coordinate vectors are related by the matrix. And if the basis is Okay. Now we know that P is PU1. PU2. PUN. Okay. So this measure representation consists columns. So the columns of this measure representation is just the image of the basis vectors in B, right? The image of all the basis vectors in B, and but you take the B coordinate. And with respect to another ordered basis, C or B, he has another measure representation. Okay. That's that. Yes. Okay, and so these two measure representations are related. By so it's from C to B. From the C coordinate system to the B coordinate system. And then the measure representation relative to basis B. And here from B. Things the inverse, right? We know this is the coordinate change, right? So the change of coordinate, right? From C to B and from B to C, they are related. They are just inverse measure to each other. So that's B. Any questions? So what I have written now, just a special case of what we discussed on Wednesday. Because we discussed a result for arbitrary linear transformation from V to W, right? So V and W can be different. So the square case is that the V and W are the same. So the domain and codomain are the same. This is the first point. The second point is that for the domain and codomain, we select the same basis. Okay? We select the same basis. So in this case, that they are very special. The metric representation relative to the basis C, and the metric representation of the operator T for the basis P are related in this way. Okay, so this is a matrix, right? This is the inverse of this matrix. We have the theorem called basis change of linear operator. Okay, so this is basic change for linear operator. So let T be a linear operator on an n-dimensional vector space. Okay, so T is a linear operator. Means that T is a linear transformation from an n-dimensional vector V to V. And let B and the C be two bases for V. Yeah? Okay, so I will erase this part. Okay, so I will erase. Then we have a metric representation of linear operator T rectus C, right? It's a relation with the metric representation of the linear operator T relative to basis B by the matrix for the coordinate of the definition. So these two matrix representation are very special because for this matrix, we have an invertible matrix here times the matrix and times the inverse of this invertible matrix. So we say that n times n matrix A is called linear to minus 1 n times n matrix B. So to be similar to denoted as A similar to B. If there exists an n times n invertible matrix E such that A is equal to P, B, B inverse. That is the definition. Right. But basically, an n times n matrix A is called to be similar to an n times n matrix, so A similar to B. If there exists an invertible n times n matrix B such that this is P. So P should be invertible, otherwise you cannot be invertible. A remark. The matrix representation of the matrix representation of a linear operator B in an n-dimensional vector space. Relative to ordered basis C similar similar to each other. So let me write down properties of similarity among n times n matrices. First property. Reflexive. A similar to A for any n times n matrix. Okay. So first of all, any n times matrix is similar to itself. Proof. A is equal to I, A, and inverse. basically I can find the identity matrix I, right? IA, I inverse is A. So A is symmetrical. Second, symmetric. If A is similar to B, then B is similar to A. Okay? Good. A similar to B implies that A is equal to B inverse for some invertible matrix. Okay? And this is implies that you can multiply P inverse here. So P can be written as P inverse A P. Okay? So you multiply P inverse here. Oh, okay. Maybe I just write P inverse A P equals to P inverse E P. This is called P. Right, so this implies that P can be written as P inverse A and P inverse again. So this is implies that P. Okay. So now the invertible matrix will be selected to be the inverse of P. Any questions? Because P inverse is called back to P again. Third, transitive. If A similar to B and the B similar to C, then A similar to C. A similar to B and the B similar to C implies that A is equal to P inverse, and B equal to Q. For some invertible matrices P and Q. Okay. So that means that A, B, and B is Q, and C inverse. And this is PQ, C, and PQ. Look. So this is implies that A. So similarity has a reflexive property, symmetric property, and transit property. So it is an equivalent relation. So similarity is an equivalent relation, or I think equivalence. I use non. And equivalence relation on the set of all n times n matrices. Any questions? Yes, please.
所以这个生物跟之前讲的那个 row equivalent 是一样的。
Different, they are different notions.
notation 一样。对，可是他们的 notation 都是这样子的。
Oh, I use the same notation? Really? Okay. So. All right. Then. Okay, I change notation. Yeah, so please, because I have erased my definition, so please put the equal sign under the material. One more here. Okay. Other questions? Yes.
那有什么话跟 row
Row equivalence. Different, yeah, they are different notions. Yeah, because first here, we say A is similar to B, right? Because they can relate it in this way. But for alright, so maybe row equivalent and the similarity. Two different equivalent relation on the set of all First of all, row equivalents are true for any rectangular matrices. So row equivalence is defined for the set of m times n matrices, right? So if they can be rectangular, not necessarily square. So this is the first distinction, right? But for similarity, we have this is only for the square matrices. Okay? This is only for the square matrices. The second thing is that even though we consider the set of all n times n matrices, okay, these two notions are different. It is that First of all, A if only if they have the same reduced row echelon. Okay? Alright, so an example is that an example, all invertible n times n matrices are row equivalent. Why? Since they have the identity as they have the same reduced row echelon form. Which is just identity matrix. So the class of the row equivalent class corresponding to the row reduced echelon form I identity is the set of all invertible n by n matrices. Very big class, right? Very big. Alright, so it's very but here A is similar to B, and if only there exists an invertible matrix B such that A is equal to B is invertible. And you will see that there are possible that two invertible matrices not similar to each other. Okay? Because you have to find an invertible B satisfy this equation. Alright, and so we have to do some elaboration on this concept, similarity later, okay, before we can have a whole picture. Because we know the row equivalents are large, right, by no operations, but everything is just to go to the reduced echelon form. And we know for any matrix, the continuous matrix, its reduced echelon form is unique. We prove that. That is the fundamental theorem we have to prove. Okay. So you can say that the reduced echelon form is just the ultimate template for row equivalence. Different reduced echelon form were corresponding to different row equivalent class. Okay, so they are representative. And the identity matrix is the basic representative for all invertible matrices. Because that for an n by n matrices, if the row retain echelon form is the identity matrix, then the original matrix A should be invertible. From chapter 3, right? We know that already. Okay, so we know this concept a lot, but we still not familiar with the similarity up to now. But we will gradually understand the notion. Other questions? Just write down what I have said. So it may happen that two invertible matrices A and B are not similar to each other. So if they are invertible, then they must be row equivalent to each other. Okay, but we will find examples that two matrices A and B, even though they are invertible, but they are not similar to each other. Maybe I will give you a quick example. Maybe I'll give you a quick example. A. Okay. B. A and B. A and B, they have determinants equal to 1, right? So they are invertible. Very easy, right? But they are not similar. You can prove by contradiction. How? If B similar to A, if suppose we just say suppose B similar to A, then there exists a P, right? Such that B, which is 1, 1, 0, 1, right? It's 1. It's P, A, E inverse, right? It's okay? But the A is identity. So this is P times P inverse. So this is identity. And so this is 1, 0, 0, 1. So you must have 1, 1, 0, 1 equal to 1, 0, 1, 0, 1. Is that true? Of course, it's a contradiction, right? So a contradiction. Right? So starting from the assumption that B is similar to A, we end up with what? B equal to A. but P is not equal to A, right? The fact is B is not equal to A. So we got a contradiction. So that's A. So it's not. Oh, I forgot. That's simple. Okay, any questions? Now, so we say that if we have two bases, right? Okay. So for any linear operator on a finite dimensional vector space V, if we choose two different bases, then the linear operator will have different metric representation relative to different bases. But we know these two metric representations are similar to each other, right? You know. What is the converse statement? Suppose we have two matrices, and these two matrices are similar to each other. Okay? Can we say that these two matrices are the two metric representation for certain linear operator? Okay? Relative to two different bases. Can we have this result? So here is the theorem. So let's A is equal to P and Q and P inverse. Okay, maybe let's say A similar to B is then check taking the column So we take the columns of P as an ordered basis. N. Okay. Because P is an n by n matrix, right? So let me write down. I have to indicate the dimension. So I take this notation to say that N, B are n by n matrices. So N and B are similar to each other, so that they are related by an invertible matrix P here. And because that the P is invertible, so the columns of P, right? The columns of P is a basis for the for the Rn. Okay, because that because it is invertible, so the column space of P is just Rn. Okay, and all the columns form a basis. So we know that fact already. So now we take the columns P as an order basis form. Okay. So when we take into that, then A, we have A, we have B equal to 1. B, it's okay for you? Basis B and the matrix B, no problem, right? But if you have problem, I change the notation a little bit. Rather I use Q, right? Q here. Q. So Q is, we have Q where P equal to 1 with dx equal to ax. So the relations here, we can use A to define a linear operator on Rn. Right? So it's a linear operator on Rn by this definition. And what is Q? Q actually is the metric representation of this linear operator relative to the basis. And the basis B it is formed from the columns of the matrix. Okay? So A is metric representation. Remember, when we write it down, we say that A is the metric representation of this linear operators relative to the standard basis. Okay? Remark. A is the matrix representation of P standard. Okay, A is the metric representation of P relative to the standard basis. Standard order basis. Okay, so the standard basis here. So A is the metric representation of this. We use A to define a linear operator on Rn, and in this case, actually A is the metric representation of this linear operator relative to the standard ordered basis. And now if we want to use another basis, so here we select the column as P as the new basis. Then relative to this basis B, the metric representation of T is Q. Right. So we construct. So basically, this is a constructive theory to show to you that whenever two matrices are similar to each other, you can interpret these two matrices as metric representation of certain linear transformation relative to different bases. So that's the idea. Okay? This is the idea. Any questions for the statement here? Alright, so let me do a proof. So let the invertible matrix P read as this way. Then the basis, all the bases, U1, U2, up to UN. Yeah. Okay? And for all vector in V, oh, not Rn. Right? X. So X is equal to alpha 1, 1 plus alpha 2, 2 prime. Is the vector, the coordinate vector, PD where B coordinate. Okay? So now we use the construction many times. So this is P, the matrix P, and this is okay. So any vector, any n-dimensional column vector can be written as the P matrix times the P coordinate. So when we write it down, this is same as writing down a unique linear combination. So every time when we write this equation, it's the same as we write this representation, the same. Okay. All right. Now, AX. So of course. AX is also an n-dimensional column vector, right? So we have P, AX. Okay? I just replace this by AX. Because AX is also a column vector, right? So AX. So AX, and what is AX? So this is P and P. Okay. So now Px is what? It's P inverse A x. Oh, by the way, I forgot to say, this is implied equal to P inverse x. Sorry, forgot to say. So the p coordinate of x is equal to P inverse times x. Okay. All right. So we have that, but we know from here P inverse A. So when we multiply P inverse on the left, P inverse A is equal to Q P inverse. Okay? So we have this identity from this equation. So now PA, P inverse A is Q P inverse X. That P inverse X is just the p coordinate of X. So this is Q, and we have done. So this one must be so the conclusion is okay, so let's take a 5 minutes break. So we come back our class 11:15. Starting from 10 o'clock in the morning. I forgot, did we change to 10 or 20? 20. And then copy. Calculate 4 to 6. Okay. Now we start a new chapter, chapter 6. Eigensystems. And there is only one section, coincidence. Okay. So okay. So this chapter will give you a basic concept of eigensystems. Okay, let me take an example. So consider a linear operator. P P1. Okay, so P1 is alpha 0. Right. So So P1 is the set of all polynomials. Degree is most 1. So that is a very simple one. Such that P1 is equal to and the TT is equal to okay, so 1 and T the standard basis know that is the standard basis for P1, right? So the constant polynomial and the monomial T is consists of a standard basis for P1. The P coordinate of a polynomial x0 plus x1t in P1 is x0 and x1. Maybe I not use okay. So okay. So this is the P coordinate of a polynomial. Like this one, right? Very simple one. And the matrix representation of P of this linear operator relative to the standard basis is okay? Yeah.
这个 T of E 跟 T of T，那两个 equation 只是举例而已吗？还是它要遵守的 T transformation 要遵守的条件
？Yeah, because we in section in chapter 5 or even in chapter 5 we state that a linear transformation can be determined by the assignment of the image for basis vector.
可是那两个有办法同时符合这两个 equation。
Yeah, no problem. Because 1 and t is a basis. You can assign arbitrary polynomial there. Because 1 and t is a basis for P1, right? P1 basis. So you can uniquely determine a linear operator or linear transformation if you assign image for the basis vectors. And this is uniquely defined a linear operator. Because because 1 and t consist of bases. If 1 and t cannot consist of bases, then it's questionable. That's true. That's true. For example, if these two are linearly dependent, then these two must be linearly independent. If these two vectors are linearly dependent, then their images must be linearly dependent. Must. Okay. Mm-hmm. All right. Okay. So this assignment actually determines a unique linear transformation, and that's why. So it's enough because the matrix representation of T replicates V is constructed in this way. So what is this? T1 is 2 transpose T, replicate basis. Tt is 1 minus T, replicate basis. Yeah. And what is that? By the coordinate here, this is 2 and 4. Okay. The first column 2, 4. And the second column is 1 and minus 1. So 2, 4, 1, minus 1 is the matrix representation of this linear transformation relative to the basis, the standard basis B. Okay? Is that okay? Yeah, this is the first example we take for the matrix representation of a linear operator. Any questions? Okay, now. Consider another basis. So this term is for B1. You can check it's really a basis. Okay, you know how to check it, right? Otherwise, you cannot answer my question on Wednesday. So this is actually a basis for P. Because these two polynomials span P1, and these two polynomials, this set is linearly independent. Okay, so now you want to find, so what is P relative to C? This is what I want to know. Right. And by our formula, what is that? We already know this one, right? That's by direct, because the basis is so simple. Basis is a standard basis, so it's very simple to know that. But for this basis, this is not a standard basis. It's a little bit complicated, right? So I don't want to compute it directly, okay? Because it takes some effort. So I use our result here. So the only thing we have to put is here, this one. Okay? Here, this one. Or, oh, maybe I can write it. I'm sorry. I just do it as an exercise. Right? So, okay, so let's compute again. So now t 1 minus t. Okay, what is this? T 1 plus t. This one. I have to use t1 plus tt. So it's 2 plus 4t plus 1 minus t. So this is 3 plus 3t. Alright, so it's 3, 1 plus t plus 3, 1 plus t plus 0, 1 minus 4t. Right. And again, t 1 minus 4t, t1 minus 4tt. So this is 2, 4t minus 4 minus t. So this is, what's that? It's minus 2t minus 2 plus 8t. And so what is this? Is 0 times 1 plus t and minus 2, 1 minus 4t. Yeah. Okay. So so what is the metric representation? The Tx C is equal to Tc. Yeah. Okay. And the Tc, the 1 plus t bracket c and the 1 minus 4t. So this is the metric representation relative to basis c. And from here, the image is expressed as a linear combination of these basis vectors. So this is, what is that? This is 3, 0. Yeah. And similarly, the image of 1 minus 4t has been expressed as a linear combination of this basis vector. So this is 0 and a minus 2. So the metric representation here is a diagonal matrix. Now you compare the metric representation of t relative to the standard basis is a little bit complicated, right? Because you have non-zero entries in the 4 positions. But if we choose this basis, then the metric representation is a diagonal matrix. So you can see that T, C is much simpler than T. And when we have a diagonal matrix as a metric representation, then the computation of the coordinate system will be very simple. Right? Very simple. So that so later on, that is T. Observe that 1 plus t is equal to 3 times 1 minus t. And the t 1 minus 4t is minus 2 1 minus 4t. So the linear operator on the basis vector becomes to a multiple of the same basis vector, right? And this is the same. The linear operator on the second basis vector is equal to a scalar multiplied with the same basis vector. So that for any pt in T1, if pt can be written as L0 and 1 plus t plus A1 1 minus 4t. Okay, so if we choose the C coordinate system, so okay, so if probably like 1 and 2. Alright? So we choose C as the coordinate, the basis, then we have a C coordinate system. And the A1, A2 form the coordinate vector. Then the PP becomes to what? Becomes to A1 P plus A2 P. So this is become to 3 times A1 minus 2 times A2. So the image can be written immediately. Alright? So you can see it's very simple, right? That so if we express PT by a linear combination of the basis vector in this spatial basis C, then the images, okay, the images can be written immediately without any combination. The 3 and the minus 2 are very special, right? Very special. A question. The question is here. Let G be a linear operator on an n-dimensional space. Can we find a basis C for V such that the metric representation relative to this basis is diagonal. So we put this question, right? So consider arbitrary linear operator in an n-dimensional space V. Can we find a basis C for V? Okay? Just like here, we find a basis, very special basis for T, and we find that the metric representation of T relative to this spatial basis comes to a diagonal metric. Okay? So this is equivalent to ask for a basis equal to V1, V2 up to Vn, right? Such that E 3I equal to lambda I Vi for all maybe too quick, maybe I'll say that so we ask that oh, okay, maybe I'll write this. What? So we show. What is Vi? Vi is the coordinator. It's Ti. Okay? Is that okay? The coordinator, the basis. Alright, for each basis vector, C, sorry, that's what you see. The C coordinate for each of the basis vector, just the standard unit vector. Okay, is that okay for you? Okay, double. Alright, that's good. So so T V C, right? Is okay, and this is VI. Okay. And what is this? This is just lambda I. So the TVI, the C coordinate is that you have, so this is what is this? So the C coordinate of the image of VI, right, has non-zero coefficient at the aspect law. So that means that T VI is equal to what? 0 times V1 plus 0 times VI minus 1 plus lambda I VI plus 0 times VI plus 1 plus 0 times Vn, right? The linear because we can synthesize the vector by using the coordinate, right? Coordinate. So this, but our coordinates, the coordinates, they are all zero except at the S position. Here. So this is lambda I. Okay. So that's why I claim here. So the question is to find a basis, right, special basis for the vector space V such that the linear operator relative to this basis, right, has such a metric representation, and this metric representation is the most simplest one you can have. Because diagonal metric representation is the most simple. Right. So to achieve that goal, it is equivalent to ask for a basis. So we want for a basis. So this is detail, right? we want a basis consists of n basis vectors, such that each vector should satisfy such an equation. All right. So here the diagonal entries is some meaning here, because they must satisfy this one. Why? Because I give a proof here. Okay? And these questions, right? So the fundamental problem is that the equation is Ex equal to number. So we are asking for solutions lambda satisfying the following equation. Okay. Because we should find a vector and a scalar such as t operate on the vector is equal to lambda. A scalar is that. Right? Because they are all the same equation. But we have to find n of the solutions. Okay? So we are asking for a general for the following general equation. Which is called the eigenequation for the linear operator. Alright, and we will talk a lot about this eigenequation in the rest of this semester, because it's so fundamental. From our previous example, we know these eigenequations may have many solutions, because lambda is unknown, x, the vector is unknown too, right? So we have unknowns for lambda, unknowns for x. They are unknown. Okay? Definition. So you know, one of the key reasons why we have to consider eigenequations, right? Okay? We want to. The reason is because we want to find a simplest metric representation for the linear operator. This is the key reason. Okay, so we try. Alright, so now if a vector non-zero vector V. And the scalar lambda real or complex. Now, the lambda later on can be, we will extend that can be real or complex. Right? Oh, by the way, I think I have to do something before I make the definition. Alright, so that we the n-dimensional vector space over R or C. So the coefficient now can be all real numbers or the set of complex numbers. Okay. And let E be a linear operator on V. Okay. Now the definition. A non-zero vector V vector space and a scalar lambda satisfying the eigenequation for T okay, so it's going to define a non-zero vector. Very important. Why we should consider non-zero vector? Because if x is 0, you can put any lambda, right? Because T0 is 0, right? For a linear operator, T0 is 0. So 0, and then you can put arbitrary lambda here. So you get a solution. So it's trivial. 0 always satisfies the eigen equation. So nothing new. So what we want is we have a non-zero vector V. Okay? And a scalar lambda and satisfy the eigen equation right here. So called eigenvalues are called an eigenvalue of T. Okay, are called an eigenvalue of T, and eigenvector of T associated with an eigenvalue. So who is, so I have to have to change the order because eigenvalue is more important than. So a scalar lambda. Sorry, I have to change. And a non-zero vector v satisfying the eigenequation for t, right, are called an eigenvalue of t. So if I find a scalar lambda here, and I find a non-zero vector v, so they must be satisfied this eigenequation at the same time. If this is true, then this scalar lambda is called, the number are called an eigenvalue of t. And the v, right, is an eigenvector of t, but also selected with an eigenvalue number. Okay? Now we have definitions, but how do we solve? How do we solve the eigenequation? How do we solve? Right, so to solve, of course, to solve the eigenequation for a linear operator T, we have to use the matrix, right? Numerical method, right? We have, for computation, we have to use the numerical method. So to solve the eigenequation Vx, put down okay, for a linear operator V. Okay. We select a basis for V. Okay? We select basis for V and consider the matrix representation V of V relative to V. Right? So this is the only possible way we can get into the numerical parts. Because we can manipulate the matrices, right? By using computers or by your hands. Because a linear operator a function is abstract. So you have to make things numerical. So the way is that you have to select a basis, whatever basis you want, right? But you can select one. It's pretty convenient for you. Right, for the domain, for the vector space V, and consider the matrix representation of T relative to V. So this is a matrix. Okay, and then so we call this as A. So A is the matrix representation of the linear operator relative to the basis. Now, so now we return. So now so Tx equal to lambda x. Right? This is our eigenequation for the linear operator T. We take all in the vector. Right? Relative to the basis B. Okay? But taking the coordinate is a linear transformation. So we know this is lambda what is that? This is equal to the basis of vector. Okay? Are we okay? So we turn this eigen equation into A which is a metric equation, and we are familiar with how to solve. This is a system of linear equations only, right? Okay. Because it's a matrix. This is a column vector and the scalar column vector. So it's just like so after the so I reserved the V because I here. Okay, so right. So now relate x to be the beta coordinate of vector V. Alright, so now I reserve x to be the coordinate vector. So now we have A x equal to lambda x. So this is called the eigen equation. The eigen equation for the eigenequation for the matrix. Okay. Alright, so we turn the eigenequation for linear operator T to the eigenequation for a matrix A. To solve this eigenequation, the same room to solve this eigenequation. Because once we find the, and so for any scalar lambda and any x satisfying x equal lambda x is called an eigenvalue of A and an eigenvector of A associated with the eigenvalue set. So we turn the general problem into metric problems that we should find. So once we find a metric representation, okay, of a linear operator relative to a basis chosen for the vector space V, then this metric representation will establish its eigenequations And from this eigenequation, we have to solve its eigenvalue and the associated eigenvectors. So before we leave the classroom today, I give a theorem here to show you we can actually solve. We can actually solve this eigenequation. A scalar lambda is an eigenvalue of A if and only if the determinant of A minus lambda times its matrix is 0. So this theorem gives us a tool to find all possible eigenvalues. Because lambda is an eigenvalue of a matrix A, even only if it satisfies this polynomial equation. You will see it's actually a polynomial equation. Okay? And the proof is that lambda is an eigenvalue of A if and only if there exists a non-zero vector x Rn such that Ax equal to lambda. Right? So this is the economic condition. So that means that A minus lambda, I think the identity operator is 0. Where I identity function. Okay? Alright, so you can move to here. Okay? So you, I don't need to that. Sorry. Identity matrix now. So I don't need to connect back to the linear operator. Just matrix, yeah, that's fine. So this is, and so that means that the kernel with x non-zero right? So x is non-zero vector. So that means that the kernel of the matrix that equals to is non-trivial. Because we have the non-trivial solution in the kernel. But this is just saying that the determinant of or maybe you can say that A minus lambda I is non-invertible. So that's the determinant. Do I use P? Yeah, I use capital P. The determinant is A. Okay, So next week we will start with this point, because now we are able to find eigenvalues already by solving this equation. This is a polynomial equation, okay? Because you have experience determinants already, so we can see. All right, any questions? So today I start a story about eigensystems. And the purpose to consider the eigenequations is because we want to find a the simplest measure representation of a linear operator. Okay, so that is the main purpose for us. And so to solve the question, we have to solve the eigenequation. And to solve eigenequation, we have to find eigenvalues as well as associated eigenvectors. But it turns out that to have all possible eigenvalues is the first step. Why? Because we have a numerical equation to solve. Okay, so that is, this problem comes to be tractable, means that we are able to find a way to solve the eigenequations. Okay, so let's start.